You ever wondered how astronomers are able to detect extrasolar planets thousands of light years away? Well, thanks to the center of mass concept, this is made possible. The center of mass is the location of balance between objects with two different masses and is always located near the heavier object. Now, a planet and its star both orbit around this hypothetical point and represents where the entire mass of the object is concentrated. This diagram represents a star and its planet bound together by gravity on an imaginary x-axis. The equation m1 times r1 equals m2 times r2 is used to calculate information about the planet. M represents mass while r represents radius. m1 and r1 belong to the star, while m2 and r2 belong to its extrasolar planet. Now here's an example of how to use the equation along with the diagram. We're given the information that the mass of object 1 is 32 grams, the distance or sum of r1 and r2 equals 55 centimeters, and r1 is equal to 16 centimeters. When we take our given information and look back at the diagram, it's evident that we need to solve for mass 2. In this particular problem, we'd use simple algebra to rearrange the equation to read mass 1 times r1 divided by r2 equals mass 2. Now once we plug in all of this information that we're given, we can solve for m2 and we get 13.13 centimeters. Now this concept is backed by simple physics. In an experiment, I tracked the movement of a system of two balls of different masses that were connected. The parabolic shape of the trajectory when thrown means that they revolved around a center of mass instead of one of the balls, which is a common misconception. And here this graph shows that same information. Here's the formula for solving the location of the center of mass. This is done by multiplying the mass of object 1 times the distance between the origin and object 1, which is represented by the teal arrow, plus the mass of object 2, the yellow one, times the distance between object 2 and the origin, represented by the purple arrow, divided by the sum of the masses. After we plug in all of the necessary information for the Sun and Jupiter, we locate their center of mass at 0.005 AU, which happens to be about the radius of the Sun. Now this concept isn't only important for our celestial bodies, but for athletes. Skiers have to be aware of their center of mass at all times to maintain stability in jumps and turns. 2014 Olympic slopestyle skier Nick Gober explained that since he cannot change or control his angular momentum when he's airborne, he must control his rotational speed. By pulling in his arms, he can increase rotational speed, while extending them decreases his moment of inertia. Now that you're all experts on center of mass, I hope that you can take this information and start locating center of mass for extrasolar planets and everyday objects. Good luck!